All right, so let's jump into Unit 3B, Day 5. We're going to start with some quadrilateral proofs. So within our quadrilaterals, we've been working for a while and we've been seeing that when we add in diagonals, we create triangles. So we could add in both diagonals and create 4 small triangles, 2 larger ones, and so on. So we will also be using some of the reasonings from last unit. So reasonings that we could say sides are congruent is if it's the given. If I said something's a midpoint, so definition of midpoint. If it is a segment bisector, so it's cutting the segment in half. Or if it's a common side, so reflexive. Okay, also I could say like if I was told it's a parallelogram, then I know that opposite sides are congruent, so that's a property I could use. So reasons angles would be congruent if it's a given, if we have vertical angles, if we have parallel lines, which when we have parallelograms, we have those. We can use alternate interior, exterior, and corresponding angles. And then definition of angle bisector. So if a diagonal bisects an angle, it's cutting it right in half. We could also use, if this is a parallelogram, opposite sides or opposite angles are congruent. So we have a lot of different options here. So let's recall the 5 ways that we can say that triangles are congruent. So we could say side, side, side. We could say side, angle, side. Angle, side, angle. Angle, angle, side. Or if we have 2 sides, we could do hypotenuse leg if we have a right triangle. That's one leg, the hypotenuse, and a right angle. Okay, so let's start here. In this first step of my proof, it says given ABCD is the shape is a parallelogram, so ABCD is a parallelogram. We don't have to write out the word, we can use this symbol, given. If we want to divide this up, we can. Step 2. So I'm ultimately trying to prove, I'll highlight it, I'm trying to prove angle ABD, this angle here, is congruent to angle CDB, this angle here. Okay. Well, if we recall, those can be considered alternate interior if these sides are parallel. Okay. Because this is a parallelogram, these sides are parallel. So I'm going to say that AB is parallel to DC because that's a property of parallelogram. So the property is opposite sides of a parallelogram are parallel. Now step 3, because I said that these are parallel, now I can say that these 2 angles do equal each other because alternate interior angles theorem. So I'm going to say angle, I'm going to list it exactly like my proof step. ABD is congruent to angle CDB. Number 4, let's go ahead and write our given. RSTU is a rectangle. UM is parallel, not parallel, equal to TM. All right, so RSTU is a rectangle. Okay. So what do I know about rectangles? I know they've got 4 right angles. I know opposite sides are congruent. Opposite sides are parallel. Okay, I've not been given any diagonals, so I may not talk about those. Okay, I also was told that UM, this piece, is congruent to TM, this piece. I'm trying to prove that RM, this piece, is congruent to SM, this piece. Okay, so I see right now, maybe even I'll grab another color here. I see that I've got a triangle built within my rectangle. What can I say about this triangle? And I have two seemingly identical. Let's see. If I could prove that these triangles are congruent, then I could prove through CPCTC that these two pieces are congruent if I have enough information. So I could talk about RU and ST, these two pieces. Those are congruent because they're opposite sides of a rectangle. So I'm going to say RU, and we're using equal signs, so I can use equal or congruent, does not matter. RU is congruent to ST. Why? Because opposite sides of a rectangle are congruent. Okay, and then my step 3, let's see here. We don't have enough information to talk about RM yet because we don't know if M is the midpoint. So we can't talk about a third side. Let's talk about angles. I don't know anything about this, so I'll angle U. However, I do know that this is a right angle and this is a right angle. So instead of saying that they're right angles, I could say that they're congruent to each other. So I can say angle R is congruent to angle S because it has 4 right angles. So all angles of a rectangle are congruent and 90 or equal 90 degrees. Either of those is fine. So now I have a right angle, a leg, and a hypotenuse. I have enough information to say these triangles are congruent through hypotenuse leg. So step 4 would be hypotenuse leg, triangle, RMU is congruent to triangle SMT. Because I know the triangles are congruent, I can say through CPCTC, I can say corresponding parts of congruent triangles are congruent. So I'm going to go ahead and say that RM should make this piece equal to this piece. RM is equal to SM, CPCTC. Okay, how could this have looked a little bit different? We could have said this as a congruent statement because that's kind of more how we did it last unit. So we could have said here, congruent, and then step 6, change it from congruent to equal. So RM is equal to SM. Why? Definition of congruence. So that's just toggling between an equal sign and a congruent sign. Okay. Either ending would have been fine. I would not have counted you wrong if you did it how we initially did. Last page here. In your picture, first off, go ahead and extend this line. It did not print there for some reason. Okay. We have this given, and I typed it up for you so it wasn't too much to write. So let's just write our given. Step 2. So AF, I'm going to start marking all over this picture now. AF right here is congruent to CF here. So that's a diagonal, it's congruent. Okay, BF here that's congruent to DF here. So the diagonals are congruent. The diagonals bisect each other. All right. And I was also given that AB, this piece, is congruent to BE, this piece. Okay. We're trying to prove that CD, this piece, even if it's not drawn to scale, is equal to BE, this piece. All right. Well, what I'm given so far is the diagonals bisect each other. Now, what is that true of? That is true of a parallelogram. So, what we've just proved here is that the ABCD, the whole shape, is a parallelogram. How do I know that? Because the diagonals of a parallelogram bisect each other. It did not say that they're all equal, so I can't say that this is a rectangle or even a square. I can't assume it's a rhombus, but it could be a parallelogram. It could still be a rhombus, but more importantly, it could be a parallelogram here. So what else do we know about parallelograms? We know that opposite sides are congruent. So if I look at AB, then I know this top side is congruent. So I know that AB is congruent to CD. Why? Because opposite sides of a parallelogram are congruent. Okay, so if I gave this AB 3 marks, then I'd have to give this 3 marks. Well, right now I'm trying to prove that these two orange pieces are congruent, and in my picture I see that they both have 3 marks. There's not really any triangles for me to say like side, side, side or anything like that. I have that, but I have nothing about this triangle outside. So let's see if we can find something else. Well, right here, I'm trying to say that CD is equal to BE. And right here I have AB set equal to 2 different things. So I can do another step and say that these 2 sides are equal to each other. If they're both equal to AB, then they're equal to each other. So we're altering the sides of the equal signs. So CD is congruent to BE. Now how was I able to do that? Well, if A equals B and A equals C, then B and C are equal to each other. That is the transitive property. Number 4, given that ABCD is a rhombus, we want to prove that triangle AED is congruent to triangle CED. So let's take a look. All right. So we're trying to prove that AED, this triangle here, is congruent to CED, this triangle here. Okay, well, let's see here. First, what do we know about a rhombus? In a rhombus, I know that my diagonals bisect each other. So I know that AC here is congruent to, AE is congruent to EC. AE is congruent to EC. So what's driving me right now? I'm trying to prove triangles are congruent. So I'm trying to get to one of these 5 reasonings. Okay, that's what I'm trying to use. So I'm attacking a side here. So I know that AE is congruent to EC. Why? Because diagonals bisect each other in a rhombus. Diagonals of a rhombus bisect each other. All right. What else do I know here? I know that I could talk about the other diagonal, but I really only need to talk about DE. DE is a common side. They both have DE. So I could say that DE is congruent to itself. And how can I say that? Reflexive. There's so many ways we could go with this next. I could talk about E being a right angle and how they're congruent. That would lead me to side angle side. I could talk about how in a rhombus, all sides are the same. Oops. Which means that AD and DC are congruent. So rhombus has 4 congruent sides. Now I have enough information to say that those triangles are congruent because I have side, side, side postulate. So triangle AED is congruent to triangle CED, side, side, side. Okay, if I had talked about the 90-degree angle, it would look just slightly different. If I didn't talk about these outside sides, and I talked about the 90-degree angle, I'd probably say something about how angle AED and CED are equal to each other because rhombi diagonals are perpendicular, meaning also they're congruent if they're both 90. Then I could say side angle side to say they're congruent. I could have used hypotenuse leg if I didn't talk about the diagonals here and I talked about all the sides. So a leg and a diagonal. And use HL. Still would need this step 4 though. Many options. Let's go ahead and do our last one. This one is a little bit tricky, and this one is pretty important. It does show up later. So ABCDEFG is a regular heptagon inscribed in circle K. So let's just go ahead and take a second and write our given. And I'll abbreviate circle K as a simple circle with a dot in it and then the letter K. All right. So if you're not done writing that, pause it for me. So being a regular polygon means that all of the sides are the same. And we don't have any letters here. So let's go ahead and just letter this. A, B, C, D, E, F, G. Okay. So I'm trying to prove that triangle BKC, I don't have a letter K, but if I put a point in the very middle of this circle, the center of this circle, I can call that K. That's because this is circle K. So the point in the very middle is how we name the circle. That's new. Now if I have B to K to C, I've created a small triangle. And these points from K to B, that's from the center of the circle all the way to the edge. Do you remember what that's called? From the center all the way to the edge of the circle? That would be called a radius. And remember, all radii where all the radius are the same measurement. They're all the same. So let's jump in first and let's just talk about what we've already done. We've already done the regular polygon part. So I'm going to say we're focusing on BKC here and CKD. So I'm going to say that BC and CD were the same. BC was congruent to CD. Why? How do I know that? Because it's the definition of a regular heptagon. Okay, so next, I have all these radii. So I know that each of these is the same measurement. They're all radii. So I'm going to say that all of these in my triangles here are congruent. So BK is congruent to CK, which is congruent to DK, because that's the definition of a radius. Okay, now I have enough to say that these two triangles are congruent because I have side, side, side postulate. So, and I'm trying to prove triangles are congruent. So step 4, triangle BKC is congruent to triangle CKD through side, side, side postulate. I definitely would star this one. Take a look back over it because it will appear again.